Hello and welcome back to Educator.com and welcome back to Biochemistry. So today's lesson, we're going to be talking about the Michaelas Menten constant and this new constant that we're going to introduce called Kcat. This particular lesson is really very important. I'm not suggesting that the other lessons are not important, but in the biochemistry course, the study of kinetics, this quantitative study of kinetics is usually sort of a daunting thing for the kids. There's just a lot of symbols floating around. There's a lot of mechanisms, a lot of reactions. You have enzyme, substrate, product, enzyme, substrate, all kinds of things going. So it tends to get really confusing. So what I wanted to do is I wanted to come back. We've already discussed Michaelas Menten kinetics. We have the Michaelas Menten equation. I wanted to go back and talk about what Km actually means. I want to talk about how it's used in biochemistry, whether that usage is actually justified or not. So I just wanted to spend some more time with it. That's it. I just want you to be as comfortable as possible because these things do come up a lot. Well, of course they come up a lot in the literature, and it's the one area that I think kids are the most that it alienates them the most easily. So it's really not that bad. A lot of it is actually quite intuitive. You just need to sort of get past a lot of the symbolism. In any case, let's just jump right on in, and hopefully we can help you to get a better understanding of what all of these different things mean. So let's see what we can do. Okay, so let's go ahead and start off with the Michaelas Menten equation again. Let's recall. So recall the you know what, I'm just going to, the Michaelas Menten equation. It said V0 is equal to Vmax times the substrate concentration over something called K sub m plus the substrate concentration. So basically what this equation does is it relates the speed, the velocity, the rate of the reaction, how fast it's going, in either moles per second or molarity per second as a function of substrate concentration, which is really very convenient. So it's such a beautiful equation. Now this Vmax, we saw already that if you're given a particular enzyme, you can keep adding substrate. You're going to increase the rate, but at some point all of the enzyme molecules are going to be completely saturated with substrate. So all of the binding sites are taken over. Now, an enzyme can only go so fast, so no matter how much more substrate you add, you're not going to make it go any faster. So from your perspective, what you see, or actually I'll draw it on here, what you see is this thing that looks like this. It ends up maxing out at some speed. There is some upper limit to how fast an enzyme can go. You can't push it any further than it will go if you have a certain amount of enzyme. Now, it's true, you can add more enzyme, but that's experimental conditions. The body doesn't just add more enzyme. The body needs to keep its enzyme concentration reasonably low because enzymes aren't used up in a reaction. So it needs to keep them low and constant. It doesn't just add enzyme whenever it wants to speed it up. It's substrate concentration that changes. So Vmax is just an upper limit on how fast the reaction will go. This Km, as it turns out, is, remember, it is the concentration at which the speed is 1/2 of the maximum speed. I didn't draw it very well here, so let me raise this one a little bit. So something like that. So that'll be Vmax. That's some upper limit that the speed is going to approach. So Km is a constant, but it has units of concentration because you remember it's concentration of substrate that's on the x-axis and its rate, its speed, that's on the y-axis. So this Km is the concentration of substrate that I need that will make the enzyme operate at 1/2 of its maximum velocity. 1/2 is just a good number. Not too low, not too high, right in the middle. That's what Km is. So this is the Michaelas Menten equation. Now, recall also from the derivation, because we did do the derivation, recall that this was derived from the following postulated two-step process. Following postulated. So Michaelas and Menten, they postulated this particular process, a two-step process. They said that you had enzyme plus substrate. There's an equilibrium that exists between that and the complex enzyme substrate once it's attached, and then that breaks down into enzyme plus product. Now there is some K1, which is the rate constant for the forward reaction. There is some K negative 1 for the breakdown of enzyme substrate back to enzyme and substrate. And then there is K2, which is the rate constant for the breakdown of the enzyme substrate complex into enzyme and product. They postulated that this was the slow step. So this was very important. They postulated that this was the slow step, the rate determining step. So when we say slow, we mean rate determining. I'll go ahead and write that down here. The slow step, the rate determining step. Because again, your reaction is only going to go as fast as your slowest. Okay, now, so let's see if we can do this. Now, Km is the amount of substrate concentration that will put your enzyme at half velocity. Well, Km is often interpreted as a numerical measure of an enzyme's affinity for its substrate. Affinity for its substrate. So you'll often see Km as interpreted as some numerical measure of an enzyme's affinity for its substrate. I'm going to show you why it's interpreted that way, and then I'm going to discuss why you have to be careful with that particular interpretation. For the most part, it's not going to be a problem as far as the problems that you do in your book or the things that you discuss in class, but it's very, very important not to just automatically assume that some Km value that you're given or that you read off in some reference book for an enzyme is a measure of the affinity of that enzyme for its substrate. So I'm going to discuss why it is interpreted that way. Let's start off there. Here is why. Okay. Now, in the derivation of the Michaelas Menten equation, if you want to go back a couple of lessons, the Km was this. It was a combination of the rate constants, K1, K2, and K negative 1. It was K2 plus K negative 1 over K1. That was the Km. The actual definition of Km is this. Our interpretation this way makes more sense intuitively because we have a graph that represents it. But this is the actual definition. It's actually a combination of the rate constants of a given process. In this case, you have a 1, 2, 3. You have a three-step. There's one this way, one this way, one that way. So it's a combination of those rate constants. Now, if K2 let me write this a little bit better. If K2 is in fact rate limiting, in other words, if that K2 step is really the slow step as was postulated, then K2 is a lot less than K negative 1. It's a slow step. So the rate constant is very, very low, very, very small compared to K1, this thing. So this is small compared to this. So the Km becomes, because K2 is so much less than K1, we can actually ignore it in the numerator. So Km becomes Km equals K to the negative 1, K sub negative 1 over K1. So this is what the Km actually becomes under these conditions. Okay, now let's investigate this. What does this mean? What does this mean? When we have the rate constant in the reverse direction divided by the rate constant in the forward direction, that's the Km under conditions that we've postulated where K2 really is the slow step and can be ignored in the actual definition of Km. Well, here's what it means. Let's go back to our equilibrium. We have enzyme plus substrate in equilibrium with enzyme substrate. This is K1, this is K negative 1. Now, the forward rate, and you remember anytime we write a rate law, it is going to be some constant times the concentration of the reactants. In the forward direction, the enzyme and the substrate separately are the reactants. So,